So I'm going to talk about 2 and 3 dimensions. In case there's any if there's any questions. Right. What is this? So I want to start by reviewing what Vlad talked about. And I'll state these 2 theorems. And then I'll talk about 2 and 3 dimensions. And I'll talk about why life is harder in 2 dimensions than it is in 3 dimensions. And then I'll try to give some idea of what we can do about it in the end. So, all right, so the surface subgroup theorem says let M3 be a closed hyperbolic 3-manifold, right? Then there exists this F from S to, well, from a surface into M3 nearly geodesic. Right? And therefore pi1 injective. So I have a 3-manifold, which I can't draw very well. And we're going to find this hyperbolic surface. And it's going to map in some highly complex way. And now, the Ehrenpreis conjecture says let S and T be closed hyperbolic surfaces. Right? Then there exists S hat, T hat, S hat and T hat finite covers of S and T, respectively, and H from S hat to T hat, a diffeomorphism of small distortion. And it's possible to make this much more precise, but small distortion, basically, it means anything you want it to mean. And the statement will be true. That there's some geometry, local geometry of S hat and T hat. There's this diffeomorphism, and it only has the slightest distortion of the geometry.
Are you assuming that S and T have the same genus?
No, because we can make S hat and T hat have the same genus. Okay, so here we're getting something nearly geodesic, and here, quite kind of analogously, we're getting something of small distortion. Right? And now the question is, well, first the question is, how can we make these theorems look a little bit more similar? Okay, so the idea basically, how shall I put this? What I want is a kind of model surface. So, well, it's going to depend on some parameter. So there's going to be some large R. It's basically the same as the R that Vlad was talking about. And there's going to be a model surface, SR. And then, I see, it's these cloths. Okay. There's this model surface. So the idea is given one surface T, right? Given one Riemann surface T, there's going to be this finite cover T hat of t, right, like we have here. And maybe I'll put the model surface up. Yeah, sorry, there's going to be a finite cover of, well, there's a few ways I could do it, but let's just do it this way. So there's going to be a finite cover of the model surface, and then a finite cover of our given surface t, and then this homeomorphism between them. Okay, this small distortion diffeomorphism. So, and then of course if I have another surface S, and I can do the same thing for that other surface S. Well, it's going to be a different cover, of course. It would be a different cover, sort of. A different cover here. But then there's a common cover here. And that means I can find a common cover here. So if I can prove that given this surface T and this model surface, I can find this Ehrenpreis conjecture condition. And I can do this, then I can do the same thing for another surface, and it means that these two have a common cover that are close to each other. All right? And the point is that another way to think about this is that I'm going to build this model surface, and I'm going to have a nearly isometric immersion. All right? So I'm going to build a cover of the model surface. I have my given Riemann surface. And then I have a nearly isometric immersion from this cover to my given surface. And the whole idea is that an isometric immersion, right, an immersion from a closed two-manifold to a closed two-manifold is a covering map. So I'm going to have a covering map from here to here. And then this nearly isometric covering map, I can form this t hat so that they're equivalent. And so now the point is that I've made this look more like the surface subgroup theorem. I'm saying given a hyperbolic two-manifold, I'm going to find a cover of this surface, of this model surface, that's nearly isometrically immersed, and therefore like nearly a cover, a nearly isometric cover of my given surface. And then down here, it's the exact same thing. I can say we're going to take the same model surface, and I'm going to do the same thing. What we actually do in 3 dimensions is we form this finite cover, and it's also nearly isometrically immersed. But of course, now it's not a cover of the 3-manifold. It's simply a nearly geodesic immersed surface. So from this point of view, the surface subgroup theorem and the Ehrenpreis conjecture become very much the same theorem. The only difference is that in the surface subgroup theorem, you're given a closed hyperbolic 3-manifold. And for the Ehrenpreis conjecture, you're given a closed hyperbolic 2-manifold. Okay, so far, we see that if you write them in the same way, where you have a nearly isometric immersion of this cover of the model surface and a nearly isometric immersion of the cover of the model surface, every word is exactly the same, and the only difference is between 3 and 2 dimensions. Okay? So let's move on to these boards. And so the question is, why is this harder in 2 dimensions? Okay, why did we prove the surface subgroup theorem first and Ehrenpreis second? Well, Vlad pretty much talked about this. So the idea is that, so what are we actually doing? Right, the first thing is we have this notion of good pants. So here's a pair of pants. And my definition will be slightly different from Vlad's. We cut it into two parts. And then we measure this half length. So we have the half length of gamma. And to be a good pair of pants, it should be in this interval. And what's this model surface? The model surface is simply the ideal we take perfect pairs of pants. Yep. So we take perfect pairs of pants where these three lengths are equal to R. Right? So that's as good as you can get. And then we have a way of assembling them. So we could take two copies of this, and we assemble it, but we don't want to just double this. We want to twist it by one. So that when you look at how geodesics come together at these right angles, you have some sort of drift, like this. And the reason we want this drift is that we have some bending or some error at each of these curves, and we don't want this error to accumulate too much in one place. So we sort of push the error along like this, and we can get good estimates. Okay? So, right, so the question of why is it harder in 2D? So in 3 dimensions, okay, in 3 dimensions, Vlad drew this picture. Yeah, it's a tricky picture to draw. I mean, it's sort of like this picture. So here's a geodesic gamma, and then there's any number of pants coming off of it. But they're coming off in all directions. They're coming off in all directions. And we want to have the pants, each pair of pants, glued to one nearly opposite to it. And there's a lot of space to doing this. So if we look at the geodesic kind of head on, so I have this picture. If we look at the geodesic head on, we can just pair things, like pair this guy with the opposite guy, pair this guy with the opposite guy, and so on. And we might have an odd number of these coming in, but if we just take 2 copies of each of them, then we can pair each pair of pants with one nearly opposite to it. Okay, so another way of saying it is that if I have this permutation, right, sigma from the pants at one geodesic to the pants at one geodesic. So the idea of this sigma is that it moves each pair of pants to one nearly opposite to it. Then I can form this sigma, well, this involution tau from this pi gamma, sort of pi gamma plus direct sum pi gamma minus. And the idea is that this is just going to do sigma, and this is going to be sigma inverse. Okay? And then you can easily check that this is an involution, and it's going to pair things with things opposite. Okay, so in 3 dimensions, it's this very simple business. But in 2 dimensions, we have this problem. Let's see. So in 2 dimensions, what are we trying to do? We're trying to take these immersed pairs of pants. It's very hard to draw a good immersed pair of pants on a surface, but the basic idea is that the pair of pants, right, there's a pair of pants way up there, but I'll draw another one over here. This pair of pants, these curves are quite long. These curves are quite long. And so there's a little thin part connecting the pairs of pants that's very long, and these kind of big, thick parts. And so this big, thick part is sitting somewhere, and then the thin parts could be sort of winding many, many times around the surface, crossing itself many, many times. But its boundary is these geodesics. And so what we're trying to do in order to build this cover, so I'm trying to build this cover, t hat of t, and I'm trying to build it out of these good pants. Okay, the theorem is that if I can build this cover, t hat of t, out of good pants, then it's going to be close to a cover of this model surface. So if I can make it out of good pants, then it's close to being a cover made out of perfect pants. Okay, it's close. That I make this thing out of good pants, and that's close to the kind of model surface where I make these pants perfect. And so what I'm looking for are pairs of pants that are on opposite sides of some given geodesic. So here I have some portion of a geodesic. I didn't want to draw the whole of the geodesic. And here I have these two pants. Here's a pair of pants on one side and a pair of pants on the other side. And this is what I'm looking for. I'm looking for immersed pairs of pants in the surface so that I can pair them off across this geodesic. They are on the two sides of the geodesic, and I want to be able to pair them off. And then if I can pair them off, I've made a cover out of these good pants. And there's some rule, again, there's some like twist. This pair of pants should be displaced in just the right amount from this pair of pants. But that all takes care of itself. It turns out the biggest problem is that I might have more pairs of pants on one side of this geodesic than I have on the other side. Okay, so I'll repeat that. I may have more I have this geodesic, and it has two directions to go in. Does this draw? No. It has, its normal bundle has two components. And I may have more pairs of pants on this side than I have on this side. If I choose some collection of pants, I may have more on one side than I have on the other side. And then I can't pair them off. It's a very simple kind of obstruction.
You mean attached with that as a boundary component, or,
Yeah, so, right, that for each pair of pants, I have three geodesics as a boundary, right? And so I have some collection of pants, and I fix a geodesic, and I look at all the pants that have that geodesic as one of its boundary components. And when a pair of pants has a geodesic as a boundary, it can be on one side of that geodesic or the other, basically giving us one direction in the normal bundle or the other component of the normal bundle. And I can only pair off guys on one side with the pants on the other side. That's because I want an immersion, right. If I flipped back, if I sort of had a surface that went this way and then flipped all the way back, I could sort of pair things with themselves. But I want an immersion, so I want to pair things on one side with things on the other side. Right? And this way, the idea is that each pair of pants is immersed. If I have two pairs on opposite sides of a geodesic, I can glue them together to be immersed. And I can continue to assemble in this way. So I have pants. Whenever I have them on opposite sides, I can glue them together to make an immersion. And if I can make this immersion with no boundary, then I've made a cover. All right, Saul? Okay.
They're immersed pants, so there's a left and a right. You can't have a half twist.
Yeah, right. It can't twist around the geodesic. Yeah, as you go along the geodesic, either the pant is always on the left or it's always on the right. That's the best way of thinking about it.
You have this geodesic, and then you pick a joint pair of pants, and then you're going to walk to one of those cups and somehow keep doing this?
Well, right. So if I do it in the kind of naive way that you're describing, I'm going to sort of infinitely add on pants, and it's not clear I'm ever going to close up. So what I want to do, maybe I should make this clear, what I want to do is I want to fix some collection. Right, so I'm going to have some collection. Well, I want to fix, I'll just write this. I have a multiset of good pants. All right, so I have this pi epsilon r is a set of all good pants isometrically immersed in my given surface S. Okay, so I have a set of all these good paths. This is a finite set. This is a finite set. The size of this pi epsilon r is about e to the 3r. Because we have 3 choices to make. So I have about e to the 3r of these guys. But what's important is it's finite. And I'm going to take a multiset, so some number of each of these good paths. And then the idea is that if I can match them up in this way at these geodesics, if I can take this given multiset, so some multiset, I don't know, M or something, right? If I can just fix this multiset once and for all, and then match it up at each geodesic, then I can build this cover. Okay, so that's the idea. So, well, let's see. All right, so I'll put this on briefly. Counting connections. So one way to think about how many paths do we have around a given geodesic, well, if I have some geodesic, a pair of paths with this geodesic as boundary, it means finding a third connection. Okay, if I have a geodesic gamma and I have this third connection, then I can thicken that a little bit and get a pair of paths. And so if we can count, and for each pair of paths, likewise, there'll be, for each pair of paths with gamma as boundary, there'll be this third connection. Right? This other way of connecting one point on the geodesic to another. So the idea is that this, here's the pair of paths, here's this third connection. Like if this is gamma, right, here's this third connection. But if gamma, if this pair of paths is immersed in the surface in S, right, this is a very schematic diagram, then this third connection could wrap around the surface in some very complicated way. But we can still keep track of it. And the number of third connections that meet it orthogonally and have just the right length is equal to the number of pairs of paths that have gamma as boundary. Okay, so there's a nice formula for the number of such connections. We just have, if I have 2 geodesic segments, alpha and beta, and I want to connect it by some segment eta, orthogonal at both ends, and I want to constrain the length of eta to be in some interval, then the number of such connections, well, this number here, it's kind of, if you were to take the average over all alpha and beta, like wherever you put them in the surface, it's relatively easy to check that this would be the average number of connections. So this is kind of the expected number of connections. And then there's some error term, and the point is that the error term grows more slowly than this. Okay, if I think of L1 as being large, so here I have e to the L1, and then here I have e to some constant less than 1 times L1. Okay, and this follows from the exponential mixing. The idea is that if I shoot out from a point here, and I start flying in the geodesic flow, then by the time I've gone for a long time, I've kind of forgotten where I started. That's what mixing means, that you go for a long time and you've forgotten where you started. And so the number of connections here is kind of the same as if I chose this alpha at random to begin with. And then that's an easy integral to do. Okay, so using the mixing of the geodesic flow, we can estimate the number of connections. And I think Margulis was the first, I don't know if you've seen this statement before, it's very similar to the statement of the number of connections between a pair of points. But we need a slightly different variant. So this is, you know, an idea, certainly, I think. Sorry? Yeah, they did something very similar. I don't know if they did literally this, but, you know, I started with Gregory and then continued with Eskin and McMullen and so forth. So returning now to this problem about boundary, right? We want to build a cover. We have some collection of pants. So we have this multi-set of good pants. We have some large collection of pants. And we want to build a cover out of these pants. And so there's a certain simple algebraic way of deciding if we have the right number of each pair of pants. So here I have, again, a very schematic diagram. I mean, I'm taking the obvious boundary operator for a pair of pants. The boundary of a pair of pants is a sum of these three oriented geodesics. And for our purposes, we want to say that if you reverse the orientation of a geodesic, then that becomes the negative in our kind of algebraic sum of geodesics. Okay? But I want to do this. I'm doing this in... so the idea is that this boundary operator, it's mapping from, well, let's say, I could take negative sums, but let's say positive sums of these good pants. Okay, so these are immersed. I should draw an S here, which I'll usually forget. I have these pants immersed in my surface S. They're isometrically immersed in my surface S, and they have three geodesic boundaries where the half-lengths are with an epsilon of R. Okay? And so I have this finite collection of good pants. And I have a boundary operator, and this takes us to integer sums of good curves. Right? The boundary of a pair of pants is a curve. Well, it's a sum of three curves. And the boundaries are good curves, pretty much by definition of good pants and good curves. They're the curves whose half-length is with an epsilon of R. And the point is that if I take, for example, I want to start with one of each pair of pants. Okay, the most basic idea is to take one of each pair of good pants. And if I take the boundary of this formal algebraic boundary of the sum of good pants, that will tell me the imbalance. That will tell me how many more pants I have on one side of a geodesic than I do on the other. Right? Because if I have some single geodesic gamma, I take the number of pants on this side, that gives me positive contributions to gamma, and I take the number of pants on the other side, that gives me a negative contribution to gamma. So this boundary of the sum of pants, kind of restricted to gamma, is equal to number of pants to the left, say, minus number of pants to the right. All right? And the crucial observation, so there's two observations. How many pants? Right, so the number of pants, the number of p pants in this pi epsilon r, such that gamma is in this boundary of a pair of pants, this number is about r e to the r. Okay, it's about of the size e to the r. Because I have some choice about where I choose these points for the third connection, and then I have about e to the r possible third connections. So the number of pants with a given geodesic as boundary is like r e to the r. But on the other hand, when I take this boundary, where I'm taking pants to the left minus pants to the right, then the number of these pants, the difference between these two numbers is much smaller. It's e to this constant less than 1 times r. Okay, so I have nearly the same number on both sides, because this mixing theory tells us that I have nearly the same number of third connections on both sides. I have this slight discrepancy, and I need to somehow correct for this slight discrepancy. All right? So what we need is a correction function. All right? Yep. Well, it's a funny projector. What we need is a correction function. So we need, I mean, let's just look at this. Conceptually, so I have this boundary operator. Like the first thing to do, right, I have this boundary operator from, well, I have it with z, but I could do it with r. Oh, it shouldn't be. Well, I guess, did I do this? Yeah, that's all right. That's all right. Okay. So this boundary operation, I mean, it's kind of funny, right? If I can write r, so that if I write r pi epsilon r, this is formal sums of good pants. And if I write r to the pi epsilon r, right, this is essentially the same thing, even though it looks totally different, because it's giving a real number to each pair of pants, and this is the same thing. That's strange, isn't it?
Want to solve any other product? You care. Oh, it's fine. It's fine.
Yeah, I don't really care. I don't really care. So it's kind of funny. I wrote it one way on this, and I'm writing it another way on the blackboard, but it doesn't really matter. So I have this boundary operation from sums of good pants to sums of good curves. I mean, I could do it with real valued or integer valued. It doesn't make much difference. And this boundary operation, I mean, it's this very simple thing. And so it's a linear transformation. I mean, in a way, it is better just to write it like this. It's just saying I have a linear transformation from one finite dimensional space to another finite dimensional space. Right? And then the problem is, right, that if I take, just naively, if I take one of each pair of pants, and I take the boundary of this, then the problem is this is not equal to 0. Okay, I can't prove that it's not equal to 0, but I certainly can't prove that it's equal to 0. And I very much suspect that it's not equal to 0. Okay, so this is the problem, and it's exactly saying that we have more pants on one side than we have on the other side. So what's the solution? There's an obvious thing to do, right? So the solution is solve, right, for boundary sum pairs of pants, sorry, P in this pi epsilon r, plus some correction term, I don't know, beta, right, equal to 0. So I'm going to have some correction term with beta small. Okay? So how small does beta have to be? Well, it should be less than 1 on each pair of pants. Right? These are numbers which are just telling us how many of each pair of pants we want. Beta should be less than 1 on each pair of pants. so that I'm guaranteed to have a positive sum. And in fact, I mean, there's some geometric technicalities I'm leaving out. We want beta to be quite small. We want beta to be quite small. But the basic idea is that we're solving a linear equation. This is a linear transformation, and we're just solving a linear equation for this beta. Okay, so how can we do this? Well, what we want to do is we want to find this correction function. So we want to find a linear transformation G from good curves to good pants. Here we have boundary from good pants to good curves. We want to find a linear transformation G from good curves to good pants. And this G should be a pseudo-inverse of the boundary operator. Okay, so if you have any linear transformation from here to here, you can always find a pseudo-inverse like this. Some very general theorem. But we also want some kind of nice control on how large this G is. Okay, and so what it's saying is that, well, recall each curve, it's somewhere up here. All right, the number of pants that have a given geodesic as boundary is kind of like e to the r. And so if we're going to take some error on a geodesic and distribute it over all pants adjacent, right, we're distributing it over at most e to the r pants. So we need G of like a single curve to be on the size at least e to the minus r. And we're saying we're doing almost that well. We allow some kind of polynomial in r term, you know, some power in r. But that's, of course, tiny compared to e to the r. So it's distributing this error sort of very, very evenly over all possible pairs of pants. Okay, that's our correction function. And then the point is that, so let me start again over here. I guess I can just keep rolling around until something comes up. So if I have this correction function, right, the idea is I let beta be minus G of the boundary of the sum of pants. So I start with one of each pair of pants. I have some boundary, let's say that's non-zero. I just apply G to this boundary, right? Then it follows that boundary beta is minus boundary of this sum. And so when I take the boundary of this sum, and I add this beta term, I indeed get 0. Okay, but on the other hand, let me make one more observation. What I know is that if I take this boundary of the sum of pants, so this is my discrepancy, and I'm saying how large is this discrepancy? Well, it's less than e to the q of s times r, right? The number of pants adjacent to a curve is like e to the r, but I have this smaller term, which is this difference. And then it follows, from my definition of G, it follows that the size of this beta term, G of this boundary, so that's like e to the minus r times this. So it's of the order a constant r to a constant times e to the q of s minus 1 times r. Right? And this here, we're saying it's less than 1. This q of s is less than 1. So this is small. This here is very small. So if we can find this correction function, then we're finished. Right? We needed to solve, don't let it get all the way down there. We needed to solve this equation with this beta small, and I'm just observing that these conditions for this correction function are sufficient to get this beta, this correction, it's some amount of each pair of pants that we're taking, and it's something very small. Okay, now it seems sort of weird. We have like non-integer amounts of pants. But there's a couple of observations. So one is that this G actually maps Q. It's not integral, but it is rational. Okay, so it does map rational sums of curves to rational sums of pants. So it follows that this beta is rational. And I can just clear denominators, okay, to get integer sum of pants. So this is the whole idea. We want to build this correction function in order to solve this linear equation. And the way to understand conceptually how we build this correction function is in terms of this good pants homology. Okay, so we look at this sums of good curves, and we say one is the sum of good curves, the boundary of a sum of good pants. Right? One is the sum of good curves, the boundary of a sum of good pants. Well, certainly we need it to be 0 in the homology of the surface. Right? It has to be the boundary of a singular chain in order to be the boundary of a sum of good pants. But what we want to prove is the opposite, that whenever a good curve, or a sum of good curves, is 0 in homology, then in fact it's the boundary of a sum of good pants. Okay, so we define this kind of, we know that the boundary of a good pair of pants is a sum of good curves. So we can take all sums of good curves modulo some boundaries of sums of good pants. And we call this the good pants homology. Right? It's just some vector space divided by quotient vector space. And we know that this kind of maps to first homology. Okay? That there's a well-defined map from here to first homology. And then the claim basically is that this is injective. So if something is 0 in first homology, then it's 0 in this good pants homology. Okay, and this is what we want to prove. And then the idea is that the functions defined implicitly in this proof will determine the correction function. So we're going to prove that a sum of good curves with the right property is a boundary of a sum of good pants. Somehow in the course of the proof, we have to more or less, well, we have to at least implicitly define what these pants are that the curve is a boundary of. So we're going to kind of implicitly define this G in the proof. And this is actually what we do in our paper. We prove identities in this good pants homology, and then we go back in a kind of commentary to the paper. Yes?
Wait, so proving this is not enough. You also need to know that you don't use too many pants.
Yes. So we have to, you're entirely right, Saul. You're entirely right, yes. So we need to first see that we've defined some function. And then we need to do estimates on this function. Yes. So we do a series of identities. In our paper, we do a series of identities. Then we go back, we look at the functions that we've implicitly defined, and we have a whole theory of estimates for these functions so that we get the estimate that we want in the end. That's exactly right. Okay. So I'm not going to talk about how we kind of take, I'm not going to talk about how we do these estimates. I just want to talk about how we prove this statement. In the remaining 10 minutes, I just want to talk about how we prove the statement that if something is 0 in singular homology, then it's 0 in this good pants homology. So I have just 3 more pages left. Yeah. So now things get a little bit weird. All right, so let's look at the schematic diagram. This is called the algebraic square lemma. Let's look at it right here. Okay, so what does this mean? So the idea is I take my surface, and now we're really getting down to brass tacks. So the first thing is we need a base point for our surface. Okay, because we have a base point, and then we can define the fundamental group. You can't define the fundamental group of a surface. You need a fundamental group of a surface with a base point. Okay, now we have a fundamental group. And what is the meaning of this diagram? Well, the idea is all four of these points represent the base point for the surface. Okay, all four of these kind of corners represent the base point for the surface. And then each of these letters, with some little arrow, is just a schematic indicator for an element of the fundamental group. Okay, so A0, A1, B0, etc. All these guys, AI, BJ, etc., are elements of the fundamental group. So they're ways of connecting the base point to itself. And then if I have any kind of cycle of these, then they also become an element of the fundamental group. So A0U B1V is an element of the fundamental group. And given an element of the fundamental group, so given any element of the fundamental group, okay, if I have some element x, I can also form the closed geodesic freely homotopic to x, right? I can let the base point slide. I get this closed geodesic. It's determined by the conjugacy class of x. So I'll give it this notation, bracket x. Conjugacy class of x, or closed geodesic for x. It's more or less the same thing. Okay, so the algebraic square lemma, it says this peculiar thing. Okay, so suppose that I have these elements of the fundamental group. I have these 6 elements of the fundamental group. And then I put them together in this funny way. So I have 2 ways of going across like this, 2 ways of going across like this. So I have 4 ways of making a kind of complete circle in my schematic diagram. And for each one of those, I can form the closed geodesic. Okay? And now I suppose, okay, so suppose that all of these guys are in my collection of good curves. So suppose that all 4 of these associated closed geodesics are good curves. Okay, they're geodesics of almost exactly the right length. Then, if I take this peculiar alternating sum of these 4 good curves, then the claim is that this will be 0 in this good pants homology. So this alternating sum of good curves will somehow bound some sum of good pants. And then there are some technical conditions here for this to be true. The idea basically, yeah, Adam?
So, I mean, is this Pant's homology, is this like an actual homology theory in the sense of Eilenberg's ski rod?
Definitely not.
No, it's just that's something that maps to H1. Is that, I mean,
Yeah.
The Pence homology, and it's equal over, it's not equal over Z to the standard Pence homology.
Well, it turns out a posteriori to be basically the same as the singular homology, like over Q.
You have HK for all, because you were only mentioning H1 here. You have connecting homomorphisms and all that.
We don't really have this kind of theory. It seems like if you have an n manifold, you could have sort of k pants for every k less than or equal to n. And you could do some sort of theory like that. And you would hope to say that that's the same again as the standard homology.
Cobordism you're doing, right? Cobordism is a generalized homology.
It's a kind of internal cobordism theory, yeah. So we're using the term homology very loosely. Yes. They're homologous through sums of good pants. Okay, Vlad.
You say
Yeah.
that you will find covers between of two surfaces that are epsilon close, but can you make a connection with the degree of these covers? Can you say how big the degree of these covers?
Yes. So, well, Vlad is asking me this, but we think we know the answer. We didn't work out every detail, but we think that the answer is, the idea is that the number of pants we need should be on the order of something like e to the 3r, maybe e to the 4r. And r doesn't have to be so big. Because we have exponential mixing, r could be about log epsilon. So we have e to some constant times log epsilon. So, well, log 1 over epsilon or whatever. So we expect it to actually be polynomial in epsilon. Right? The degree of the cover should be polynomial in 1 over epsilon.
1 over epsilon.
In 1 over epsilon, yeah. Laurent polynomial.
So,
Yeah, so,
you just have a single good curve.
yes.
And you apply g to that, and then you get some real, well, you said rational combination which has the right boundary. I mean, can you throw the...
G can take negative values, right? If I take a single curve and then I apply this correction function, right, this g over here, I can get positive valued pants and negative valued pants. G can take negative values, right? So if I just had a single curve and I apply this correction, I don't have any nice cover. I have positive pants and negative pants whose like boundary is this curve. Is that, I'm not sure if I answered the right question.
Well, I was wondering if you were finding something that G spans, which is made out of units. You can actually capping off. Is there a way to see the capping off surface?
Capping.
I think the answer is
Oh, okay, right. You're saying, right, you're imagining I have the pants, I have some discrepancy.
yeah.
So I fit them together as well as I can so I get this immersed thing. And then I want to cap it off to be a closed thing. But it's not capping it off. What it's doing is it's reversing sometimes. It's going back over some pants. But because I have kind of many more copies, I have this large sum of positive pants, and then I take some more, less, some more, and I have to kind of reassemble it to make a closed surface. It's just a fact of life. Yeah, so I need this like field, this sort of positive field of pants in order to apply the correction. Yeah. Otherwise, yeah, it doesn't follow just from the correction theory. I need this equidistribution as well.
No more questions.
Thank you.